as we move towards solving some differential equations with power series, you need to be adept at manipulating power series, and so there are basic operations that I want for you to be able to do on them. One is addition, and the way addition happens is term by term, right? So if cosine of x is this power series here, and if cosh x, hyperbolic cosine, is this power series here, then cosine x plus cosh x is just, I add up the terms. 1 plus 1 is 2. The x squared terms cancel out because I have minus here and plus here. The x to the fourth terms reinforce each other, so I get 2 times x to the fourth over 4 factorial, and so on. Subtraction happens the same way, but with the signs flipped, right? If I want to subtract them, I literally just have to replace my plus here with a minus and carry out the algebra. Multiplication. So if we have a term such as 1 plus x squared, and we want to multiply it by this power series here, what we can do is just distribute the prefactor. So this would be 1 times the power series plus x squared times the power series. And then we can attempt to bring these coefficients inside the power series. So multiplying by 1 does nothing here in the first term. That's easy. Multiplying by x squared here, that's going to raise the power of x by 2. So I can bring the x inside, and my x to the n's I'll turn into x to the n plus 2. You need to understand what happens with the radius of convergence when you're operating on different power series. So for addition, subtraction, and multiplication, the radius of convergence is at least as big as the smallest radius of convergence being operated on, right? So, to make this concrete, say you are, say you're adding 2 power series, and the first one has radius of convergence equals 2, the second one has radius of convergence equals 17. When you add those 2 power series, you're guaranteed that the radius of convergence is at least as big as the smaller of these. So without doing any work, you know that the radius of convergence of the sum has to be at least 2, and if you wanted to know more, you would have to actually study the power series, do something like try to apply the ratio test. Another important operation that you need to get comfortable with for solving differential equations is index shifting. And the index here in the sum is just a dummy variable. Okay, so you got to get this idea into your head. So, for instance, if we start with this power series, the sum from n equals 1 to infinity of x to the n, that is mathematically equivalent to the power series j equals 1 to infinity of x to the j. Those are the same thing. You've just changed the name of the index. Changing the name of the index doesn't matter. Now here's index shifting. There's nothing special about starting with 1. We could write this power series in a different way. We could write it as the sum from j equals 3 to infinity of x to the j minus 2. Notice what we did here. We took this expression and added 2 to it. So instead of starting at 1, we're starting at j equals 3. But to compensate, we took all the j's inside the expression, inside the summation, and subtracted 2 from them. So if you actually wrote this power series out by term, starting with j equals 3, the very first term would be x to the 3 minus 2, that's x to the first, that's the same as it was in the original form. So this is called index shifting. Let's do another example. Suppose we have the sum from n equals 1 to infinity of n over n plus 1, x to the n minus 1, plus the sum from n equals 1 to infinity of 1 over n squared, x to the n. And what we're going to do is first take the first summation and index shift it so it starts at 0. If I want it to start at 0, I have to subtract 1 here from the starting value, and to compensate, I'm going to add 1 to n inside here. So this gives me the sum from n equals 0 to infinity of n plus 1 over n plus 2, x to the n minus 1 plus 1, which is just x to the n. Okay, and then I've left my second term the same here. let's see, we can go ahead and note that maybe we would like these two terms to both start with n equals 1. That might sometimes be convenient for us. So I'm going to break out the first term from the first summation separately. So I notice that if I plug in n equals 0, I get 1 over 2 times x to the 0. That's just a half. So I'm pulling out that first term, and then I can write the remaining values of the summation as n equals 1 to infinity of n plus 1 over n plus 2 x to the n. And then I still have my second summation here. And then if I want, I can notice that I have two summations. They both start with n equals 1, and they both have powers of x to the n, so I can combine their coefficients, so I can write this in the form 1/2 plus sum from n equals 1 to infinity of this expression here. Again, there's nothing earth-shattering I want you to take away from this, other than that you have the power to shift indices and write power series in different forms if it's convenient for you. Let's see, for most of the power series you're going to experience, you can differentiate them, and the way you can differentiate them is term by term. So if we take the power series cosine x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on, we can differentiate cosine x by differentiating the power series. So the derivative of 1 is 0, derivative of x squared over 2 factorial is x, and so on down the line, and we get this power series, and you might recognize this as the power series that's the negative of sine x, and that's good, because the derivative of cosine is negative sine. Here's another example which I think is kind of cool. When you take the power series for e to the x, 1 plus x squared over 2 factorial, and so on, and you differentiate it, the first term goes away, because the derivative of 1 is 0. The derivative of x is 1, that's what you had over here. The derivative of x squared over 2 factorial is x, that's what you had over here, and so on down the line. And since you go on for infinity, when you differentiate the terms, you get back the same thing you started with. And so what you've shown is that the derivative of e to the x is e to the x. And when you're doing differentiation on a power series, it turns out that the radius of convergence is going to be the same as for the original power series you started with. So in other words, the power series for cosine up here and the power series for negative sine here, these things have the same radius of convergence. Finally, the last operation or property that you need to get comfortable with is the comparison property, meaning that if you have two different power series centered around the same point, the only way those power series are equal to each other is if each coefficient in the power series is equal, right? The coefficients of the x to the 0 terms are equal, coefficients of the first degree terms are equal, coefficients of the second degree terms are equal, and so on. That's it for now. You're going to put these to work later, actually solving differential equations using power series. Thanks for listening.